Thank you, everyone. Again, welcome. I would like to start with our first keynote speaker, Dr. Alex Luhmann. The title of his talk that he's going to talk is Towards Neuroscience in Everyday World Using Multimodal Brain Imaging, Progress and Challenges. Just a very brief biography of him is Dr. Alex Luhmann is currently the Director of the Research and Development Division at NIRX Medical Technologies.
So the very short summary of the performance is just that it rejects, so using this with the GLM rejects the physiological nuisance signals much more strongly. And what we did here is we used synthetic HRFs to know a ground truth, and against that, we could measure correlation, RMSE, and F-score for our reconstructed HRF. Despite all the motion going on, basically, we would improve the metrics significantly over the GLM with regular or standard short separation analysis. So this itself could be a whole talk, so I apologize if this was a bit fast.
So our second keynote speaker, Dr. Lei Ding, the title of his talk is Novel Patterns of Human Brain Network Dynamics Revealed in Multimodal Neuroimaging Techniques. A little bit about his biography is Dr. Lei Ding is a presidential professor of biomedical engineering, electrical and computer engineering, and neuroscience, and director of Institute for Biomedical Engineering, Science and Technology at the University of Oklahoma. He's also...
So this is our framework. We still do the EEG, and we still do the ICA similar as before, and we also do the inverse. And then we actually upgrade our correlation tomography to the regression tomography. In the interest of time, I'm not going to discuss the details between these two, but the major function performed by the correlation and regression in this framework is very similar. But after that, we actually add another step called K-mean, clustering. Basically, we look at this, each bar indicate one time frame from each individual, and as the time courses for the ICA, we detect the above, and then we just do the clustering on each time frame and try to identify the spatial patterns for time frames they are similar to each other.
So the title of his talk will be a statistical analysis method for combining multimodal neuroimaging data. A little background about him. Dr. Hooper is an associate professor of electrical and computer engineering at the University of Pittsburgh. He has authored over 100 papers on FNIR's brain imaging and analysis techniques.
All of our data, this is just one time course, but we took, I think, 20 subjects here, and we started to look at what explains the variance in the data. And what you end up finding is about 70% of the variance between fMRI and NIRS is shared. Of that shared variance, about 50% of that is related to things like this, single trial variability. Only about, it's hard to read the numbers here. So only about a quarter of the noise could be said, well, this is definitely cardiac or respiratory or blood pressure that's showing up in both modalities. Says that a lot of what we're calling noise is actually probably in saying something interesting about the brain. What was unique about these two trials that were different from the other trials? Okay. And then about 20%, depending on which one you're looking, 20 to 30%, I'm sorry, it's not showing up here, was actually independent. So it was noise that we only saw on the NIRS that we didn't see in the other modalities. Okay, but about 70% of the noise is shared between those two.
Okay, and our last keynote speaker, Theresa Vaughan. So the topic of her talk will be brain-computer interface for communication for people with severe motor deficits, prospects, and problems. So Theresa Vaughan have been having many years of experience with brain-computer interfaces, specifically for patients with severe motor deficit, particularly patients with amyotrophic lateral sclerosis.
So wearable technology, we were talking about wearable technology earlier. The whole idea that this wearable industry is moving very fast, that this cap, which is now almost obsolete because there are better caps even, But this cap has stable, good signals. It's made by wearable sensing, and it gives us very good signals. That's something that needs to be developed. This computer, what do you need this computer for, right? I mean, you could use, but of course you do need a computer, but they can be put on tiny chips. So this kind of stuff can be done.
So just a very brief biography about Dr. Bahram Borghei. He is currently a postdoc researcher in the Department of Neurology at Emory University. He has got his second PhD in biomedical engineering at Neural PC Lab, University of Rhode Island. He has also been a research fellow and intern in neurology department at Massachusetts General Hospital.
So one thing which is important with reporting is you can double the sampling rate. The way at least Narex works, I don't know about Shmatsu, but the way it works that each sequence or each sample of recording, it starts sequentially from one source to the last source, and then measures, for example, for source one, it emits the light and gets the signal for that source, then goes for the next source. So if your montage is kind of symmetrical and separate in two regions of the brain, you can double it. You can say that, okay, one emitter on my left hemisphere emits at the same time with another emitter or source in my right. So in this way, you can say that, okay, for example, source 1 and source 9 emit together. In this way, you can double the sampling rate if it's helpful. In our design, we can't because we don't have two separate regions for.
Everyone, so let's move forward with our last presentation and speaker, Dr. Adam Noah. So a little bit about the background of Dr. Adam Noah. So he's a research faculty member of the Brain Function Laboratory in the Department of Psychiatry at the Yale School of Medicine.
This is 30-second block. This is single subject data. And you can see here, red is face oxy response, and magenta, this color here, is face deoxy response. And you can see dark blue and light blue show similar responses, but more noisy. And that was interesting to me, in that the area that we're recording from here, which is an occipital, temporal occipital lateral area, shows a strong response, but it seems to be more selective for face than for object, which, okay, that's fine. And here's the ERP, 100 to 200 milliseconds. You can see the time course of this compared to the near signal. You can see the red is the face, the blue is the object, and this is as expected. So this is just fiducial stuff. We were happy. We built a system that could record both signals. So yes.